Welcome to the lecture series of signals and systems. In the last lecture, we have seen few examples related to the inverse Laplace transform. In this lecture, we will include some more examples based on the convolution property of the Laplace transform, and by using this property, we can easily calculate the output of a system which input is given in the time domain and output is also given in the time domain. So we will extend our discussion by including few more examples. The one example says that here x of s is given as x of s has some value, and we have to calculate the inverse Laplace transform by using this relation. So x of s is given as s plus 1 upon s cube, s plus 1 upon s cube plus 6s square plus 4s square plus 6s plus 4, 4s square plus 6s plus 4. This is what the value of Laplace transform of xt is given, where this x of s is the Laplace transform of the signal x of t. By using this relation, we have to get the inverse Laplace transform of this x of s, which is equal to x of t. So, to get the Laplace transform or to get the xt back from the given relation, we have to apply the concept of inverse Laplace transform. And to apply, first we have to break this function in a manner by which we can apply the concept of inverse Laplace transform. So for that purpose, I will take the factor of the denominator. For that, because it is a cubic expression, we have to use the trial and hit method for the different values of s. So I will select a value of s for which this denominator becomes 0, and s equal to minus 2 will satisfy this condition. If I will put s equal to minus 2, this will become minus 8 plus 4 into 4, 16 minus 12 plus 4. So this minus 20 and plus 20 will cancel each other, and this will become 0. It means that s plus 2 will be a factor of this polynomial. If s plus 2 will be a factor, so this can be written as x of s is equal to s plus 1 upon s plus 2 here will be a factor of this polynomial. So what will be the other factor? We have to, because this is a cubic expression, so we have to get the s cube somewhere in the given relation. So this I will multiply with s square, so that this s and s square will become s cube. When this s square is multiplied with 2, this will become 2s square, but we need here 4s square. For that purpose, we have to put another 2s here. So this 2s square plus this 2s square will become 4s square. Now we want here 6s, and what we are getting is 2s into 2, 4s. For that purpose, we have to multiply with, we want to another factor of 2s. So here we will get 2 into 2, 4s plus, when I will add 2 here, this will become 2s from here, and 2 into 2, 4s from here, this will become 6s, and the constant term will become 2 into 2, 4. Now this expression is this is a cubic polynomial. This can be factorized in this way. So this can be written in the form of partial fraction as for a upon s plus 2 plus bs plus c, bs plus c upon s square plus 2s plus s square plus 2s plus 2. Now we can get the value of a very easily by putting s equal to minus 2 here. By putting s equal to minus 2 in this expression and hiding this term, we can get the value of a. So a will be equal to minus 2 plus 1 upon 2 is minus 2 square 4 minus minus 2 into 2 4 plus 2. So this will become minus 2 plus 1 minus 1 by 2. This will become minus 1 by 2. And to get the value of bs plus c, we have to compare the numerator of both sides. So this will become a into s square plus 2s plus 2 plus multiply this with this will become bs square plus 2bs plus cs plus 2c. This is the numerator of this side when they will get multiplied. So numerator of right hand side will become like this. Now consider the terms having s square only. So this will become s square. We will get a from here, another s square here. So this will become plus b plus s. So we will get 2a from here plus 2b from here plus 2b plus c from here. So this is power of s power 1, and now we will get constant term as from here we will get 2 times a, and from here we will get 2c, 2a plus 2c. So on comparing the numerators of both the side, this will be equal to 2s, this will be equal to s plus 1 as given in the question. So if this will be equal to s plus 1, it means that the power of s square, constant of s square will be equal to 0. It means that a plus b will be equal to 0. It implies that b will be equal to plus 1 by 2, because a is minus 1 by 2. From here b will be equal to plus 1 by 2. And also if from the power of from the comparison of s power 1, we will get 2a plus 2b plus c, the power of s power 1, the coefficient of s power 1 is 1 here. So this will be equal to 1. Value of a is known. This is minus 1 by 2. So 2 into minus 1 by 2 will become minus 1 plus 2 into 1 by 2 will become plus 1 plus c equal to 1. It implies that value of c is equal to 1. So from here we got all the coefficients a, b and c as a equal to minus 1 by 2, b equal to plus 1 by 2 and c equal to plus 1. Now put these values in the given expression. So x of s will become x of s will become equal to a is equal to minus 1 by 2. So this will become minus 1 by 2 into 1 upon s plus 2 plus p is 1 by 2 here. So 1 by 2s plus 1. 1 by 2s plus value of c is 1 divided by s square plus 2s plus 2. This is how x of s can be expressed in the form of partial fraction. So by using this method, we can now convert this into, this is equal to minus 1 by 2 upon s plus 2 plus this will become s plus 2 upon 2 into s square plus 2s plus 2, or further this can be simplified as minus 1 by 2 upon s plus 2 plus here it is s plus 2 upon 2s square plus 4s plus 4. This can be further written as, this can be further written as 2s plus 2 square. If I will put it as 2s plus 2 whole square, so this will become 4s square plus 4 plus 4s, or so by comparison with 4s plus 4 is here, it is only 2s square. What we need is, if this will become 4s square, so this will become the square of 2s plus 2, or we can simply take 2 common from, it is fine to have 2 common from the term s square plus 2s plus 2, it is more better. So if I will write it as whole square of s plus 1, so this will become a square plus 2s plus 1. So s square plus 2s plus 2 is here, and what we need is plus 1. So simply I have to subtract 1 from here. So I can write it as plus 1 plus 1. So this will become s plus 1 whole square plus 1. So I will write it as minus 1 by 2 upon s plus 2 plus s plus 2 upon 2 into s plus 1 whole square plus 1, s plus 1 whole square plus 1. And further, if there is s plus 2 here, so I have to make this s plus 1, as we have to convert this in the form of sinusoid or cosine, as we see in the relation in the form of sinusoid or cosine. So this will become s plus 1. I will write this as s plus 1 plus 1, and now this will become minus 1 by 2 upon s plus 2 plus 1 by 2 into s plus 1 upon s plus 1 upon s plus 1 whole square plus 1 plus 1 upon s plus 1 whole square I can write this in this way. So now from here this will become, but I will take the inverse Laplace transform. This will become minus 1 by 2 e power minus 2 t ut plus 1 by 2. This will become e power minus t into e power minus t into s upon s square plus 1 means cos of t plus this will become 1 upon s square plus 1 means sine of t ut. This is what we will get by taking the inverse Laplace transform of the function. So this will become 1 by 2 e power minus 2t plus 1 by 2 e power minus t cos t plus 1 by 2 e power minus t sin t ut. So somehow we have to convert this in the form of for which the Laplace transform is known, as it is converted in this way, for which we can write the inverse Laplace easily. This is the trick to get the inverse Laplace of a polynomial of higher order. Now consider few examples to apply the concept of convolution theorem in the Laplace transform. As we discussed in the previous lecture also, if the Laplace transform of x1 of s is x1 of t is x1 of s and Laplace transform of x2 of t is x2 of s, then the Laplace transform of x1t convolution with x2t will be equal to, with the Laplace transform of x1t is x1 of s and Laplace transform of x2t is x2 of s, then the Laplace transform of x1t convolution with x2t will be equal to simply x1 of s into x2 of s. This is the convolution property of the Laplace transform. And by using this relation, we can find the convolution of x1t and x2t as Laplace inverse of x1 of s into x2 of s. We can use this relation to get the convolution of two given signals. So in this context, the first signal x1 of t is given as sine of 3t ut. x1 of t is given as sine of 3t ut and x2 of t is equal to x2 of t is equal to cos of 2t u of t, cos of 2t u. Now we have to get the convolution of these two signals x1t with the x2t. For that purpose, what we need is, we need the Laplace transform of x1t and we need the Laplace transform of x2t. Then we will multiply these two signals x1 of s into x2 of s. So Laplace transform of this will be equal to omega upon s square plus omega square, and Laplace transform of this will be equal to s upon s square plus omega square means square of 2. So this will be equal to 3 upon s square plus 9. This is x1 of s, and s upon s square plus 4. This is x2 of s. To get the Laplace transform of their convolution, we have to multiply these two symbols simply. So this will be equal to 3 by s square plus 9 into s upon s square plus 4. Or this simply can be written as 3s upon s square plus 9 into s square plus 4. This is the Laplace transform of x1 of t convolution with x2 of t. But this is the Laplace transform of the convolution, and what we need is we need the convolution of x1t and x2t. For that purpose, we have to take the inverse Laplace transform of this term. And to get the inverse Laplace transform of this term, first we have to convert this term. Suppose this is x of s, which is equal to 3s upon s square plus 9 into s square plus 4. So to get the inverse of this, first of all we have to use the concept of partial fraction. So I will write this expression as as plus b upon s square plus 9 plus cs plus d upon s square plus 4. This is how we can convert this expression in the form of partial fraction. For the remaining question, what we have to do is we have to get the value of these coefficients a, b, c and d. To get the values of these coefficients, the concept is same. We have to compare the numerators of both the sides. So here the numerator is 3s. So 3s will be equal to 3s will be equal to, multiply these two, this will become as cube plus 4as, as cube plus 4as, as cube plus 4as plus bs square plus 4b plus bs square plus 4b plus, here it is cs cube plus 9cs, cs cube plus 9cs plus it is ds square plus 9b, ds square plus 9b. Now take the common terms from here. So first I will take s cube common. This will become a plus c. So this will become a plus c. Now take s square common. So this will become b from here and d from here. So this will become b plus c plus s power 1. If I will take s power 1 common, I will get 9c from here plus it is 4a from here. So 4a plus 9c. Now write the constant term, which is equal to 4b plus 9. 4b plus 9b. Now compare the power of s in both the sides. So s cube is not there. It means that the coefficient of s cube means a plus c will be equal. Now S square is also not there in the left side. It means that the coefficient of S square will be equal to 0. So B plus D will also become 0. Now S power 1, coefficient of S power 1 is 3 here. So the coefficient of S power 1 will also become 3. It means that 9C plus 4A will be equal to 3, and coefficient of it is also not there in the left side, so the coefficient 4B plus 9D will also be equal to 0. By using these relations, we have to get the values of A, B, C and D. So from here we can write C is equal to minus A, and if I will put C is equal to minus A here, if I will put C is equal to minus A here, so this will become minus 9A plus 4A is equal to 3, minus 9A plus 4A is equal to 3. So from here A will be equal to minus 3 by 5. If A is minus 3 by 5, then what will be the value of C? Then C will be equal to plus 3 by 5. So A and C, these two are known, and now we can put B equal to minus D here. From here B will be equal to minus D. So when I will put B equal to minus D, this will become minus 4D plus 9D equal to 0. From here D will be equal to 0, and also if D is 0, then B will also become 0. So we got all the values of A, B and C. A is equal to here minus 3 by 5, and B is equal to 0, C is equal to plus 3 by 5, and D is also 0. Now substitute all these values in the given expression of x of s. So we will get x of s as x of s will become minus 3 by 5 into s upon s square plus 9 plus b, and b is 0. So leave the term b and write plus c is equal to 3 by 5 into s, 3 by 5 into s plus d is 0, s square plus 4. This is what we got from the partial fraction of the given expression. Now write this in the way as this is equal to minus 3 by 5 s upon s square plus 9 plus 3 by 5 s upon s square plus 4. This is what we got the Laplace transform of x1t convolution with x2t, and to get the convolution of x1 of t with x2 of t, we have to take the inverse Laplace transform of this given relation, minus 3 by 5 into s upon s square plus 9 plus 3 by 5 into s upon s square plus. We have to get the inverse Laplace transform of this term to get the convolution of x1t with x2t. So this will become, if I will compare with the Laplace transform of cos of omega t ut, that is equal to s upon s square plus omega square. In place of omega, it is omega square, it is written 9 here. So it means that this can be written as minus 3 by 5 cos of, in place of omega, it is 9. So this will become cos of 3t ut plus 3 by 5 into cos of 2t ut. After comparison, we can write it in this way. So this is the finally result for the convolution of x1t with convolution of x1t with x2 of t. This is the result for the convolution of x1t with x2t by using the convolution theorem of the Laplace transform. The next example says that x1t is given as tut and x2t is given as u of t minus 2. Example number 3 is given here as x1 of t is equal to tut and x2 of t is given as u of t minus 2. For these two equations, we have to get the convolution of x1t with x2t by using the convolution theorem or convolution property of the Laplace transform. So, for that purpose, what we have to do is, first we have to get x1 of s, means Laplace transform of tu, and this will be Laplace transform of tut will be 1 upon s square. 1 upon s square, and Laplace transform of u of t minus 2 means x2 of s will be equal to e power minus 2s upon s, because it is the property of shifting in time domain. The Laplace transform of ut is 1 upon s, then Laplace transform of ut minus 2 will be equal to e power minus 2s multiplied by 1 upon s. Now, the Laplace transform of their convolution means Laplace transform of x1t convolution with x2t will be equal to x1 of s into x2 of s, means e power minus 2s upon s cube. To get the convolution of x1t with x2t, we have to get the inverse Laplace transform of e power minus 2s upon s cube, and because e power minus 2s is multiplied here, it simply indicates that the signal in the time domain will be shifted by 2 units to the right, means the signal in the time domain will become, if it is xt, this will become x of t minus 2. So suppose whatever is the signal, we have to put t equal to t minus 2 in that. So this will become Laplace of, inverse Laplace of 1 upon s cube, where t will be equal to t minus 2, because e minus 2s is multiplied here. So we know that the Laplace transform of t power n ut, very important relation. Laplace transform of t power n ut will be equal to factorial n upon s power n plus 1. By using this, we can find 1 upon s cube here in the denominator if the value of n will be equal to 2. For that purpose, if n is equal to 2, then Laplace transform of t square ut will become factorial 2 upon s cube, 2 by s cube. But here we are getting only 1 by s cube. To convert this into this form, we have to simply multiply and divide with 2. Divide and multiply with 2. This will become the t square ut. So this will be equal to x1 t convolution with x2 of t will be equal to 1 by 2 into t square ut, where t will be equal to t minus 2, or this can be further written as x1 t convolution with x2 of t will be equal to 1 by 2 times t minus 2 whole square into u of t minus 2. This is how we can find the convolution of two given signals by using simple properties of the Laplace transform. T minus 2 whole square by 2 into u of t minus 2. Now consider another example in which both the signals are given as u of t minus 2. x1 of t is given as u of t minus 2, and x2 of t will also given as x2 of t is also given as u of t minus 2, and we have to get the convolution of these two signals. So the procedure is simple. First of all, we have to get the Laplace transform of x1 of t as x1 of s is equal to e power minus 2s upon s, and again x2 of s will be same as e power minus 2s upon s. And what we have to do in the next step, we have to multiply these two signals. Their multiplication will become e power minus 4s upon s square. And to get the convolution of these two signals x1t and x2t, simply we have to take the inverse Laplace transform of e power minus 2s upon s square, or simply this is e power minus 4s. Because it is multiplied with e power minus 4s, it means that the signal in the time domain will be shifted by 4. So in place of t in the time domain, I will put t minus 4. So this will become inverse Laplace transform of 1 upon s square, where t will be equal to t minus 4. And Laplace inverse of s square will be t, where t is equal to t minus 4, or this will be equal to t minus 4c. So this is the convolution of these two given signals, u of t minus 2 and u of t minus 2. The next one is two signals are given as tut and tut. So the x1t is given as x1 of t is given as t into u of t, and x2 of t is given as t times u of t. And what we have to do is we have to get the convolution of x1t with x2t. For that purpose, what we need is we need the Laplace transform of x1t and Laplace transform of x2t. To get these Laplace transform, we know that the Laplace transform of tut is 1 upon s square. So both the Laplace transforms will be equal to 1 upon s square. This is 1 upon s square and this is also 1 upon s square. So the convolution of x1t and x2t have Laplace transform equal to 1 by s power 4. These two will be multiplied. 1 upon s square into 1 upon s square will become 1 upon s power 4, and x1 of t convolution with x2 of t will be equal to Laplace inverse of 1 upon s power 4. Again, compare with this relation that t power n ut have the Laplace transform equal to factorial n upon s power n plus 1. So we need s power 4 here. We need s power 4 here. For that purpose, n will be equal to 3. Means this will be equal to Laplace transform of t cube ut. This will be equal to factorial 3 upon s power 4 or 6 upon s power 4. For that purpose, we have to multiply with 6 in the numerator and we have to divide with 6. Now this will become 1 by 6 into t cube ut. By using this property, we can find the Laplace transform convolution of two given signals x1t and x2t. Now next question is the x1 of t is of a system. Input for the system is given as e power minus t ut. Input for a system xt is given as e power minus t ut, and the impulse response ht of the system is given as e power minus 3t ut. ht is given as e power minus 3t ut. Now we have to get the output of this system yt by using time domain approach and also by using convolution property of the Laplace transform. So first of all, we will use the convolution property of the Laplace transform to get the output, which says that if the impulse response of the system is h of t and input of the system is xt, then output of the system will be equal to x of t convolution with h of t. And we know the property of Laplace transform that the Laplace transform of this convolution means xt convolution with h of t will be equal to x of s into h of s. X of s is the Laplace transform of e power minus t ut and h of s is the Laplace transform of e power minus 3t ut. So x of s will be equal to 1 upon s plus 1 and h of s will be equal to 1 upon s plus 3. We have to multiply these two. So Laplace transform of yt will be equal to 1 upon s plus 1 into s plus 3, which can be written as partial fraction as a upon s plus 1 plus b upon s plus 3. To get the value of it, simply I will put s equal to minus 1 here. So this will become 1 by 2. A will become 1 by 2. But I will put s equal to minus 1 in this relation. This will become 1 by 2. But I will put s equal to minus 3. This will become, b will become minus 1 by 2. Because minus 3 plus 1 will become minus 2. So this will be equal to 1 by 2 into 1 upon s plus 1 minus 1 by 2 into 1 upon s plus 1. And to get the yt, simply we will take the inverse Laplace transform. So y of t will be equal to inverse Laplace transform of this relation. This will be equal to 1 by 2 e power minus t ut minus 1 by 2 e power minus 3t. This is what we will get by using the convolution property or frequency domain approach of the Laplace transform. Now, for that same, we can use the time domain approach also. The conventional method of finding the convolution of two signals. We can use direct formula as convolution of x of t and h of t will be equal to minus infinite to plus infinite x of tau h of t minus tau d tau. This limit is from minus infinite to t. X of tau into h of t minus tau d tau. Or so x of tau will be equal to x of tau will be equal to e power minus tau u of tau, and h of t minus tau will be equal to e power minus 3 into t minus tau u of t minus tau d tau. Here ut will exist, u of tau will exist only for tau greater than 0, and u of t minus tau will exist for t minus tau greater than 0 or tau less than t. So tau should be greater than 0 and tau should be less than t, means this limit now will become from 0 to t e power minus tau into e power minus 3 t minus tau d. The remaining is simple. Now from here we can write it as limit from 0 to infinite e power minus tau and e power minus 3t e power minus 3t. This limit is from 0 to t e power minus 3t into e power plus 3 tau d tau. Because we are integrating with respect to tau only, so the term e power minus 3t will become a constant and come outside of the integration. So this will become e power minus 3t integration of this will become 0 to t and this will become e power minus tau plus 3 tau. So this will become e power 2 tau d tau, or this will be equal to e power minus 3t integration of this e power plus 2 tau will be equal to e power 2 tau by 2. Limit is from 0 to t, and further after putting the limit this will become power minus 3t and put tau equal to t. This will become e power 2t by 2 minus e power 0 by 2 means minus 1 by 2. So this will become e power minus 3t into e power plus 2t. This will become e 1 by 2 into e power minus t minus e power minus u of t. This is what we will get by using our conventional approach or time domain method to get the convolution of two signals. So this is all for this lecture. In the coming lectures, we I may include some examples, some more examples based on this verification in the time domain and frequency domain approach, and also we will include the solution of differential equations in the coming lectures by using the Laplace transform technique. So this is all for this lecture. Thank you.